Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 1 of the video series on radicals, and we will be introducing the concept of a square root and how to perform operations on expressions containing them. So without further ado, let's go on to the first slide. The first thing we need to do is to discuss the basic laws of radicals, aka square roots. We start off with part A, which is the definition of a square root. We call the number A the square root of B. Again, we call the number A the square root of B. If and only if, that's what that symbol means, if and only if A squared is equal to B. Okay, so again, A is called the square root of B if and only if, when you square it, you get B back. That's provided we adhere to these restrictions, that A and B must be both greater than or equal to 0. If B happens to be less than 0, by the way, B is called the argument of the square root. The inside of the square root is called the argument. Often we abbreviate argument as arg, A-R-G. So when the arg is less than 0, for example, if b happened to be -1, the square root of -1 is undefined because we cannot think of any number whatsoever such that something squared will give us -1. Okay, because we already know that a positive times a positive will give us a positive, definitely not negative. And a negative times a negative will give us a positive as well, definitely not negative. So when we see something like the square root of -1 or the square root of -2, etc., etc., those square roots exist only over the complex plane, okay? So they're called imaginary numbers, and we will not be discussing imaginary numbers at this point. It's a very, very important field, but it's the wrong place to discuss them now. Okay, so you would have to adhere to these restrictions. A and B have to be greater than or equal to 0, and this is actually the definition of what it means to be a square root. Let's go to the first square root law, which is B. A is just the definition of square root, and B, it says when we have the square root of A squared, we get identically equal to A. So the square root of A squared is identically equal to A. The triple stroke means identity, and all of these are in fact identities. The left-hand side is identically equal to the right-hand side. Okay, so these are not equations, but they are identities, and that's what the triple equal sign stands for. Again, the restriction has to be that A has to be greater than or equal to 0. Okay, if we don't do that, what happens if A, for example, is -2? We have -2 squared is 4, the square root of 4 is 2, and this would have been -2. And of course that doesn't make sense. So we need to restrict A to be greater than or equal to 0. For example, the square root of 5 squared, the square root essentially cancels out the 2, and we get a 5. So this effectively is a cancellation law. The square root cancels out the 2, and you get the inside. Okay? Again, the square root of 5 squared is equal to 5 is a typical example of that. C, when you have root A dot root A, you get A exactly. So root A dot root A is identically equal to A. Again, the restriction, the argument has to be greater than or equal to 0. An example, root 3 dot root 3 is equal to 3. Root 3 dot root 3 is equal to 3. D, when we have brackets, square root a all squared. Again, this is another cancellation law. When we have brackets, square root a all squared, that 2 cancels out the square root, and we get a itself. Again, this is only valid if a is greater than or equal to 0. The argument of the square root has to be greater than or equal to 0. Example, bracket square root 5, close bracket to the power 2 will always give you 5. Okay, so you can look at these examples carefully on your own. I'm going to go on to the next slide. The next law, if you have the square root of a product, it's the product of the square roots. So the square root of a product is the product of the square roots. Restrictions, both arguments have to be greater than or equal to 0. Okay, so you have to adhere to these restrictions. Otherwise, you start getting into complex numbers, and we're only dealing with real numbers at this point. Complex numbers is effectively out of the domain of this video. Outside that domain, okay? That's a whole other kettle of fish altogether. So we have the restrictions, a comma b, which are the arguments of this radical and this radical. We have to impose the condition that they're both greater than or equal to 0. An example of this would be the square root of 6. 6 can be decomposed as 2.3, and then again you can split it right where the dot is. You get root 2 dot root 3. Okay, so the square root of 6 can be decomposed as the square root of 2.3, and that's equivalent to root 2 dot root 3. So this is like a decomposition property. Let's look at f over here. The square root of a over b is identically equal to root a over root b. Okay, so the square root of a quotient is the quotient of the square roots. Again, the restrictions are on the arguments. A has to be greater than or equal to 0, and b has to be greater than 0. If b is equal to 0, this quotient is undefined because we have division by 0, and therefore you have to impose that restriction that b has to be strictly positive. A can be greater than or equal to 0, but b has to be strictly greater than 0. Example, square root of a quotient is the quotient of the square roots. So the square root of 5 over 7 is equal to root 5 all over root 7. The next law. If you have a compound expression like a dot root b, this is called a mixed radical times another mixed radical. I call the guys on the outside, like a is a good guy and b is a bad guy, because the square root is effectively a jail. Okay, this guy's outside the jail. He's visiting the convict inside the jail. Okay, so this is like your mother visiting you when you're in jail. This is another mother visiting another, let's say the daughter this time, because not only guys that go to jail, daughters go to jail as well. This is like a mother visiting the daughter's in jail, and the mother's visiting. So we have a compound radical here, or it's also called a mixed radical. When you multiply mixed radicals together, you multiply the good guys together, in other words, the mother with the mother, and you multiply the son and the daughter together. Okay, so you multiply the good guys together, a dot c, and you multiply the bad guys together, b dot d. Okay, so it's a dot c square root b dot d. Again, anything that remains inside the radical, I think of the radical as a jail. It's the easiest way to think about it. And then anybody outside the jail is merely visiting the convict that's inside the jail. Okay, restrictions. The arguments have to be greater than or equal to 0. Of course, b is the argument for that square root. D is the argument for this square root. The arguments have to be both greater than or equal to 0. Here's an example. We have 2 root 2. Okay, there's the good guy, there's the bad guy inside the jail, and we have 3 root 5. There's the good guy, there's the bad guy inside the jail. And what you do is multiply the good guys together. You get 2 dot 3, which is 6. and then 2.5, which is 10, but it's also in jail. Okay, so those are the basic laws of radicals. This slide contains the important perfect squares chart for reducing radicals. This chart is very, very important when you're trying to reduce radicals. The first row over here is the set of perfect squares, starting off with 1. But it's better to look at the second row to see how we generate perfect squares. If we square every element of the second row, we can generate perfect squares. Like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, etc., etc. Okay, now, SpongeBob over here loves to be a perfect square. Why? Because when SpongeBob goes to jail, he can easily escape the jail. And of course, the jail is the square root. Okay, so when SpongeBob is in fact equal to a perfect square, he loves it because he can find his way out of jail and come out here with us. Okay, so essentially we're always looking for perfect squares. And that's how we reduce radicals. So why are these nice? Because the square root of a perfect square is always a whole number. Okay, these are all natural numbers, so the square root of a perfect square is always going to be a natural number. And that's why this table or this chart is so very important for reducing radicals. Okay, and you can think about this as a square root chart, because the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, square root of 25 is 5, etc., etc. Okay, so if you can sort of try to memorize this set of perfect squares, it would be a very good idea when you're reducing radicals, because it will really, really help you out. If you can do it without looking, it's great. If you must look or you're writing a test and you can't remember, you can easily develop your own perfect squares chart by writing all the natural numbers down here and then squaring them all up here to produce perfect squares. So this will come in very, very handy. Let's go on to the next slide. And in question 1, we're going to be using the bullet target method, or the distribution property, to expand expressions containing radicals. Here's a little note. A equals square root b, if and only if a squared is equal to b. Restrictions, a comma b is greater than or equal to 0. Of course, we always have to keep this in mind. This is in fact how square roots are defined. Okay, so a is called the square root of b if and only if a squared is equal to b. Again, we have to restrict that a and b are both greater than or equal to 0. So we're only dealing with positive square roots over here. None of this plus or minus the square root of b or anything like that. Key formulas, or aka identities, we've already seen these, but I wrote them down again. Root a dot root a is equal to a. Restriction, a greater than or equal to 0. Example, root 3 dot root 3 is equal to 3. And then we've got mixed radicals over here, a dot root b dot c dot root d. You multiply the good guys together, you get a dot c. And you multiply the bad guys together, you get root b dot d. And again, you have to restrict the arguments b and d of the square roots. So b and d have to be greater than or equal to 0. Again, some examples, 3 root 2 dot 2 root 3. Multiply the good guys together, you get 3 dot 2, which is 6. Multiply the bad guys together, you get 2 dot 3, which is 6. But it's underneath the square root. This is key to learning how to reduce radicals. If you ever see something like the square root of a perfect square, times b. You can always extract the perfect square from the radical because the square root of a squared is just equal to a. And you can write a dot root b. So this is effectively what we use to reduce radicals. Again, the restrictions on a and b, both a and b have to be greater than or equal to 0. So for example, if we have the square root of 18, what's the largest perfect square? What's the largest perfect square that goes into 18? Of course, the answer to that is 9. If we go back to the perfect squares chart, what's the largest perfect square that goes into 18? It's 9, okay? So initially you might have to refer back to the perfect squares chart. Feel free to do so at any point in time. And I'm going to go back. And so we have the square root of a squared dot b. The a squared can be extracted outside the square root. There's that SpongeBob I was talking about before. He loves being inside the square root because he knows he can break loose. Okay, so the square root of a squared dot b is just a dot root b. The restrictions, a comma b is greater than or equal to 0. B just remains a bad guy because he can never get out of jail because he is not a perfect square. Again, the square root of 18 is the square root of 9.2. 9 is a perfect square. The square root of 3 squared dot 2. And of course, the square root of 3 squared is just 3. So we get 3 root 2 as the reduced form of the square root of 18. Another key formula over here when dealing with radicals is that when you have conjugate pairs, recall that these are conjugate pairs, okay? Whenever you have conjugate pairs and you were to multiply it out, you have 2 bullets and 2 targets. If you expand this, it's easy to find that you get a minus b, okay? So whenever you see conjugates, minus sign, plus sign, and these are conjugates, and you have root a, root b, for sure, when you expand the entire expression, you'll wind up getting a minus b. Okay, so whenever you multiply conjugates together, you will remove all the radicals. Okay, so this is a very, very important property. Okay, that's the way we remove radicals, by multiplying by the conjugate. Restrictions, both arguments a and b have to be greater than or equal to 0. So example, you get if we have bracket root 3 minus root 2, dot bracket root 3 plus root 2, we recognize these as conjugates. You can do it the long way by expanding. Okay, you get root 3 dot root 3 is just 3, and then root 3 dot root 2 is just square root of 6, and then you get minus root 6, and then you get minus 2, and then the root 6 is canceled because you have plus root 6 minus root 6, and you wind up getting 3 minus 2. Or you can use this property right here as long as you recognize that these are 2 conjugates. So when you multiply conjugates together, it effectively removes the radical on both. Okay? So again, root 3 minus root 2, root 3 plus root 2, they're conjugates. So all you do is erase the radicals and put a minus sign in between. Remember, it's a minus sign, never a plus sign. So we get a 3 minus 2, which is 1. Voila. We're going to do some practice questions at this point. Let's look at part A. We have bracket root 2 plus 5, dot bracket root 2 plus 5. We recognize these as this is actually a perfect square because we have an apple times an apple. So it's a perfect square. However, we're going to use the bullet, target method or distribution to expand this out. Okay, so bullet, target just means distribution. Okay, that's my way of saying distribute. We have 2 bullets and 2 targets. If we launch the first bullet, root 2 dot root 2 is just 2. Root 2 dot 5 is just 5 root 2. Notice we put the good guy out front. We leave the bad guy to the right and the good guy comes on the left. That's just convention. And then we launch the second bullet. 5 dot root 2 is just 5 root 2. And then finally 5 dot 5 is just 25. Now we want to collect like terms. We have good guys. That is to say, the good guys do not have radicals attached to them. And then we've got bad guys. So we open up a good guy bin, drop in a 2, drop in a 25. There are no radicals here. That's why I call them good. Then if we look over here, we have a root 2. So we open up a root 2 bin and we drop in all the coefficients belonging to root 2. We drop in a 5 and then we drop in a 5. That's how I collect like terms. Because some of these expressions, I don't have really, really long expressions in these exercises, but there are some that are very long. And if you use backward bin gathering, it helps you sort things out readily. So again, we simplify inside each bracket. We get a 2 plus 25, which is 27. 5 plus 5 is 10, so we write down 10 root 2, and voila, we're done. Let's look at part B. Again, we have a binomial over here. We have another binomial over here. So we have a bullet, bullet, target, target. We're going to distribute. So we have a 2 root 2 dot root 2. The root 2 is just 2, so 2 dot 2 is 4. And we write down 2 dot 2. Okay, let's do it again. We have one good guy, and then root 2 will give you 2. So we get 2 dot 2. Then we have 2 root 2 dot negative 4 will give you minus 8 root 2. And then we go on to the second bullet. We get 4 dot root 2 is just 4 root 2. And then 4 dot negative 4 will give you minus 16. And then we collect like terms. I didn't bother using backward bin gathering here because it's very easy, so I did it on the fly. We get a 4 here, minus 16 is minus 12. And then we get minus 8 root 2 plus 4 root 2. That's like minus 8 apples plus 4 apples will give you minus 4 apples. Okay, so we get minus 12 minus 4 root 2 as your final answer. So we can go on to the next slide. Again, part C over here, the same sort of thing. We have a set of brackets here. We have a bullet, bullet, and then target, target. We're going to use the bullet, bullet, target, target method in order to expand. Okay, so let's start. Root 3 dot 5 is just 5 root 3. And then root 3 dot root 3 dot 5 dot root 2 is just 5 root 6. Okay, so let's do it again. Root 3 dot 5 dot root 2 is just 5 root 6 because root 3 dot root 2 is just root 6. And then we go on to the second bullet. We get 2 dot root 2 dot 5 is just 10 root 2. And then we get 2 root 2 dot 5 root 2. 2 dot 5 is 10. And then root 2 is 2. And now we can use backward bin gathering to collect like terms. We have good guys and bad guys. And let's see now what we have. We open up a good guy bin. The only non-radical term is 20. And then we close up the bin. And then we have a root 2 bin because root 2 is a bad guy. And we drop in a 10. And then root 3 is another bad guy. And we drop in a 5. And root 6 is another bad guy. And we drop in a 5. Okay, so it turns out that all the bad guys are all different anyway. So now all we have to do is simplify by rewriting these coefficients, 5, 5, and 10, out front because that's the convention we use. So altogether we get a 20 plus 10 root 2 plus 5 root 3 plus 5 root 6. Now whenever I have a string of radicals like this, I always like to order them from lowest to highest. That's just a preference that I have. You know, mathematically it means nothing, but, you know, it just looks more pretty when you organize them from left to right, from low to high. Okay, so again, we're going to look at D. Again, we have 2 bullets and 2 targets. And we're going to be launching the first bullet. 3 dot root 5 is just 3 root 5. And then 3 dot negative 5 is minus 15. And then 2 root 5 would just be 2 dot 5 because we know that root 5 is just 5. And then 2 root 5 dot negative 5 is just minus 10 root 5. And now we collect like terms. This is a very easy one, so I didn't use backward bin gathering here. We get a minus 15 plus 10, which is negative 5. and we get 3 apples minus 10 apples is minus 7 apples. So we get minus 5 minus root 7 root 5. Or minus 5 minus 7 root 5. Okay, let's go on to the next slide. And we have E, the same sort of thing. Now I see that these are conjugates, but instead of using that conjugate formula I gave you at the start, we can always use a bullet, target, in order to see that the radicals really are gone when these two terms are conjugate pairs. Okay, so let's do it slowly. We have 2 bullets and 2 targets. We have a 1.1, which is 1. Then 1 dot negative root 5 is just minus root 5. And then root 5 dot 1 is just plus root 5. And then root 5 dot minus root 5 is just negative 5. Okay, you'll notice minus root 5 plus root 5, they cancel. And you wind up getting 1 minus 5. Well, actually, I did it slowly over here so you'd see it. Open up a good guy bin, and I put in a 1 minus 5. And then I open up a root 5 bin, which is obviously bad. And I got a negative 1 plus 1. Okay? Now, negative 1 plus 1 is 0. So the root 5 is actually gone. It's not there. So you get 1 minus 5, which is minus 4. Which just confirms that when you're multiplying conjugate pairs together, the radicals disappear. So conjugate pairs annihilate the radicals, and you get negative 4. Let's look at F. I believe that's the final question in this, or the final part in this question. Again, we have 2 bullets and 2 targets, and we're going to start firing bullets at targets. We get a 4 dot root 7, which is just 4 root 7, and then 4 dot 1, which is 4, and then minus 3 root 7 dot root 7 is just minus 3 dot 7, because you'll recall that root 7 is just 7, and then finally minus root 3 root 7 dot 1 is just minus 3 root 7. If we collect like terms, over here we have 4 good guys. We have 4 minus 21, that'll give you minus 17. Okay, so it contains no radicals, so I call it a good guy. And then we have 4 apples minus 3 apples will give you 1 apple, so we get root 7. So altogether we get minus 17 plus root 7, and I think we're done with this slide. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.